So we're going to go ahead now and look at 4.1, and we're going to begin, it looks like, with question number 1. And this involves exponents. We need to make sure that we know when we subtract, when we add these exponents, and when we multiply. And we also need to remember when we write our final answer, we do not want negative exponents. So in our final answer, we want to make sure that our exponents are positive at the end. So the first thing we want to look at on this problem is we look at our numbers out in front. These are called our coefficients out in front. So we have a -3 and a -4. And those simply multiply together. A little bit too, let me get it just about right. I think that's about as best as I can get it. So those two are going to multiply together. Negative and negative makes it a positive 12. Then we look at the x's, okay? And there's no x to a power way up top. They're just across the middle here. So when they're like that, they add together. So when we look at the x's, what do we have? We have an x to the 5th and an x to the 9th. So those are going to go together and make it x to the 14th power. And then what about the y's? Well, there's no number, so we assume that power is 1. So we have 1 y here. 2 more, then makes it y to the 3rd. So what's your answer then going to be? Your answer is going to be 12 x to the 14th, y to the 3rd power. Okay? Is everyone okay with that one? Next, we're going to look at question, it looks like, number 6. So question number 6, we have to be careful as to how we approach this one. Now, we cannot just take the 10 minus the 4. Why not? Well, before we can subtract these, remember, order of operations states that exponents must be done first. So these exponents are negative, so we're going to rewrite them as a fraction. So I can rewrite this 10 to the negative first as a fraction, and that's going to be 1 over 10. And I can rewrite that 4 to the negative first. Well, I can rewrite that as 1 over 4. Now we can see that these are fractions, and we're going to be subtracting them. And whenever we subtract fractions, remember, we have to have a least common denominator. So what's the least common denominator of 4 and 10? Can someone tell me? The least common denominator of 4 and 10 would be 20, right? Because 20 is going to both 4, and it'll go into 10. Now we'll use that. We can't clear the fractions because we don't have an equal sign. The only time you can clear a fraction is when you have an equal sign. So we don't have one, so we have to work with them. Our least common denominator is going to be 20. So we need a 2 over 2 here. And we need a 5 over 5 here. So that is then 2 over 20 minus 5 over 20, which then gives you a minus 3 over 20 for your final answer. So what did we have to do? Well, before we can subtract, remember, order of operations states that exponents must be done first. And anytime we have a negative exponent, what do? We have to rewrite it as a fraction. So we rewrote those as a fraction, and then we subtracted them. Next, we'll look at 7. For question 7, we've got a 5 over 2 to the negative 3rd power. There's 2 ways to work with this. We can either flip the fraction at the beginning, or we can just simply distribute that negative 3 through. I'm just going to go ahead and distribute the negative 3 through. And then I'm going to rewrite this as 5 to the negative third over 2 to the negative third. And what happens with these negative exponents? Negative exponents, they get flipped around. So this one's going to go down. This one's going to come up. So that gets rewritten then as 2 to the third over 5 to the third. And 2 cubed, can someone tell me what 2 cubed is? Okay, 2 cubed is going to be 8. Not 6, because you're not multiplying those together. You're writing it out 3 times. So 2 cubed is 8. And 5 cubed is 125. So what's my final finished answer? 8 over 125. Now you could have also flipped it around at the beginning and made that a positive 3, then distributed it through. You'll get the same result. But at some point in time, because this is negative, you're going to have to flip the fraction over. You can either do it at the beginning or do it after you distribute. Question 9. Question 9, we've got parentheses, and we're going to have to distribute through. Now, whenever we distribute that 4 through, those powers are going to multiply because it's out on the top here, behind on the top. So that means when this 4 goes through, okay, it's going to have to be multiplied with the powers. With this negative 2, we've got to be careful. Use parentheses around the negative 2. So that's going to be negative 2 to the 4th power. And we'll work that out to the side in a moment. Then we've got W, and we've got 7. Now these are going to multiply because the power's up top outside the parentheses here. So 7 times 4, that makes it a 28. Down below we have 4, and there's no number, so we know there's a 1 there. So 4 times 1, that makes an x to the 4th. And what do we know about negative 2 to the 4th? Is that going to be a positive or a negative number? Okay, positive, right? How do I know? Well, write it out. 4 times. You can also remember the fact that it's an even power, and even powers come out positive. If you multiply these together, you get 4 times 4, which is then positive 16. So my final finished answer would be 16, w to the 28th over x to the 4th power. Now, how do I know that I can stop here? Well, we need to make sure we can't go any further. Okay, the 16, nothing can combine with it. We have a w and we have an x, which have different bases, so they can't go together. And we do not have any negative exponents. So that's when we know we can stop. No negative exponents and all the different variables. Question 14. We're going to have to distribute, again, a negative exponent through. What I would do on 14 is I would work the inside out first, and I would try to condense it down as much as possible first. I think it's easier to work with the inside first than just distribute through and have to do it later. So this is what we've got. Now you could just distribute this negative 2 through each piece and then clean it up later. I think, though, it's easier if we break down the inside first. And besides, order of operations tells us to do the parentheses first. So let's look inside the parentheses, and we're going to work with the x part first. So on the x part, we've got an x cubed over x to the negative fifth. So what are we doing with these x's here? We are dividing, right? And when we divide, what happens to our exponents? They're going to subtract, right? Okay. So these exponents are going to subtract. So that's going to be x to the 3. Watch out for double negatives. Minus a minus 5 power. Double negative makes this now positive. So my x part is going to come out to be x to the 8th. Then we do the y part. And for the y part, we have y to the negative third over y to the 4th. So these again subtract. And that's y to the minus 3 minus 4 power, which is y to the negative 7th. Now you could go ahead and put that y to the negative 7th down below, but I'm not going to do that right now because it's just an extra step. I usually like to flip those around and bring them down below at the end. So I usually work with the negative exponents at the very end. That way I'm not moving several times. Okay, so now we've got this to here, and we've got that negative 2 still outside that parentheses, so that's going to have to be distributed through. And so when I do that, I'm now left with 2 to the negative 2nd power. We're left with, when we multiply, 8 times negative 2, that's negative 16. For the y's, double negative makes it a positive 14. Now, what about that 2 to the negative 2nd power? Well, 2 to the negative 2nd power, I can rewrite that as 1 over 2 squared. And what do we know about 2 squared? Well, 2 squared is a 4. So we know when we rewrite this that we've got a 4 down below. We don't need the 1 unless everything else is gone, but there'll be stuff left with it. Okay, so we just put that 4 down below. We don't need the 1 again unless there's nothing else there. And there's going to be more on the top because the y to the 14th will stay there. Because it's positive, so it stays up in the numerator, up at the top half. The x to the negative 16, well, it's a negative power. So where does it go? It goes down below to the denominator. And we rewrite that as x to the 16th power below. And it becomes positive. So it flips around and it becomes positive. So what's my final answer going to be? It should be y to the 14th power divided by 4 down below, x to the 16th power, also down below. Okay. Is everyone all right with that? So why did we multiply? We multiplied these powers here. Why? Because this 2 is up top. It's outside the parentheses and on the top. Okay, so that's 14. We've got 3 more of these to look at. And the next ones are going to be scientific notation. So we're going to be looking at question 22. And on these it says, express your answer in scientific notation. We're going to read the question, and we're going to think about what our answer's going to be. If it's going to be a short amount of time in this case, or a long amount of time. So a computer can do a calculation in 1.4 times 10 to the negative 7th of a second. So it does it pretty quickly. How long would it take it to do a trillion calculations? 10 to the 12th power. Well, what do I know about this? Well, I know the computer can do things pretty quickly, right? But it's still going to take a little bit of time to do a trillion calculations. Several seconds at least, because this is a negative seventh here, but this is a positive 12. So there's quite a bit of a difference. So it should take it a couple of seconds at least, maybe a minute or two to do these calculations. So that means when we work with these, we're going to have to divide, okay? And how is this going to work? Well, sorry, we won't divide. We're going to have to multiply. Okay, so when we look at this, we've got how long it takes the computer to do a calculation. So how long does it take a computer to do one calculation? To do one calculation, it takes 1.4 times 10 to the negative 7th power. Okay, that is one calculation. Okay, yep, no problem. So to do one calculation, it takes that long. Now, how many calculations are we going to have it do? Well, in this case, we want it to do 1 trillion calculations. And so this is 1 trillion. And how many seconds are in a trillion? Well, what power would that be? That would be 10 to the 12th power, right? Okay, so this is one calculation. That's how fast the computer takes to do it. We're going to do 1 trillion of these calculations. So we know it should take some time. It's not going to be instantaneous because 1 trillion is a really large number. And when we work at these, what happens? Well, these exponents are going to add together. And so that's going to be 1.4 times 10 to the minus 7 plus 12, which is then 1.4 times 10 to the, when we add these together, 5th power. And that's going to be in terms of seconds. Let's see if that makes sense. So this is our answer, but let's convert this to standard notation so we can see that it actually makes sense. So what would this be in standard notation? Well, in standard notation, we would have to move this 5 places. So there's my decimal. So there's 1, 2, 3, 4, 5. Okay, so there it is. So that's 140,000 seconds. And how many minutes would that be? Okay, if we go ahead and just divide that by 60, it's going to take a little bit of time. We knew it was going to take some time. We knew it was not going to be instantaneous. And if we divide that by 60, for the 60 seconds in a minute, right, we get about 2,333 minutes. Or about, what if we divide that by 60 again, 60 minutes an hour, or about 38.8 hours. So it's going to take some time. Now, we knew it was going to take some time. It was not going to be instantaneous, right? Because 1 trillion is a really large number. Even though the computer can do things relatively quickly, you're having it do a lot of calculations, 10 to the 12th power. These add together, right, because we're multiplying, because this is one calculation, and we multiply it by how many calculations it has to do, which in this case is 1 trillion. Those exponents then add together. And I like to convert it just so you see what it really is, because this doesn't make much sense to us. But we can understand that, hey, it's going to take about 38 hours to do this, which is a long time, but that makes sense because we're asking for a lot of calculations. If we would have done it incorrectly and you would get something that is less than a second, it wouldn't make sense. Right? Because it's going to take way more than a second to do these calculations. On these applications, the main part is making sure that your answer makes sense. If it doesn't make sense, you got to go back and look and see, did I multiply when I should have divided, or was there something else I should have done? So now let's go on and look at question 24. So question 24, we're looking at the distance from the sun to the Earth in terms of meters. Now, first off, do we think that's going to be a really large number or a really small number? Should be a really large number, right? Because number of meters not very much, and we're going to try to see how many that's going to be to go to the sun. So we're going to approach it kind of like what we did on the last one. This one's going to be a multiplication again. So when we look at this one, we need to know how many meters are in 1 mile. So in 1 mile, we have 1.61 times 10 to the third, right? Because lots of meters are in a mile. Meters is not much, right? So it's quite a bit. Several thousand meters are in a mile. And this is 1 mile, and we want to take this and we want to multiply it by how far it is to the sun. I'm going to go ahead and convert it. So when we look at this, I'm going to go ahead and convert this over to the side to scientific notation. So this is the distance to the sun in terms of miles. And we can either convert it now or convert it later. We'll go ahead and convert it now. There's our decimal point. And there's 3. 3 more. And then 1 more after that. So when I convert that, that would be 9.29 times 10 to the 7th power. And that's going to be the distance from the sun to the earth. So we're going to multiply. And we know we should get a really, really large number too, because what do we know about a mile compared to a meter? Well, a mile is a lot bigger, right? And there's going to be a lot of meters in a mile. So our answer should be larger than this, because this is in miles. When we convert it to meters, it's going to be a bigger number because meters are smaller. So now we just go ahead and multiply. And we'll multiply the numbers out in front. So 1.61. We'll multiply that by 9.29. And you can round a bit here. I'm going to go ahead and round this to 3 places. Okay, 3 places should be more than enough. You could probably get by with 2, but we'll just do 3. And this is going to be 14.95. If we round, it looks like 7. And that's not in scientific notation yet, but it will be in a moment. And then it's going to be times 10 to the 3 and 7 makes it 10th power. Now, this again is not in scientific notation, is it? It's not in scientific notation. Why not? Because for it to be in scientific notation, it has to be a single digit followed by the decimal point. So to make this into scientific notation, we're going to have to add 1 place to that. And that's going to add 1 to this exponent here. So now our answer in scientific notation would be 1.4957. Close enough there. We can round to 3 places if you want as well. But this will work for my answer here. And that's going to be times 10 to the 11th. And that's going to be in terms of meters. And you could have rounded this to 3 places if you would have wanted to. You really wouldn't want to do 2. I rounded up here to 3 so I could get 4 at the end. But 3 places, 4 places is fine. Either one's, it's fine. Doesn't specifically tell us how far to round to. So that's question 24. So now we're going to move on to the last one that we asked about, which is 25. And that makes sense because that's a lot of meters. And that should be, because when we look at the distance from the Earth to the Sun, that's a long ways. So it's going to be a lot of meters. Okay, 25. the national debt of a small country, it looks like that's going to be about 6.4 trillion, it looks like there. And the population, well, let's see, is it trillion or billion? Let's see. Let's see. There's, yep, billion. Okay, so that's going to be the debt, right? So basically $6.4 billion in the debt. And we've got, 2.3 million people. What is the amount of debt per person? Now, when we see this per means divide. Okay, so when we look at this, we're going to have to take our debt and we're going to have to divide it by the number of people. Should come out to be a fairly small number, even though it's a really large amount of debt. We're dividing it over everyone. So it should be quite a bit less than the 6.4 trillion. So let's go ahead and write up our ratio here. And I'm going to first convert these to scientific notation. And our ratio is going to be debt per person. So the debt is going to go on the top. And the number of people is going to go down below. And that makes sense because the more people the country has, the more they can spread the debt out, and the less each individual person has to contribute. If I convert this debt here, how many zeros do we have? Well, we have 3, 6, 7, 8, 9, it looks like, right? So it looks like that's going to be, if I rewrite this in scientific notation, 6.4 times 10, and make sure we count it correctly. So 3, 6, 9, so times 10 to the 9th power. And how many people do we have? If we look at our population here, looks like when we move, there's 3, 6, and so that's going to be 2.351. That's going to then be times 10 to the, 1, 5. Sorry about that. 1, 5, not 5, 1 there. Let me write it correctly here. Sorry about that. 1, 5. Okay, so it's going to be 2.315. And that's going to be times 10, it looks like, to the 6th power. Okay, now we just simply divide them out. So we'll take our 6.4 and we'll divide that by the 2.315. And that comes out to be, we'll just go 4 places. 3 places will be fine, but 4 places I think will be more than enough. So that's going to be 2.7646 if we round. These exponents are going to subtract, so that's going to be times 10 to the 9 minus 3, which is 3rd power. And it's already in scientific notation, and that's going to be how much each person owes. I always like to convert it to make sure that it makes sense. So this is our answer in scientific notation. But let's convert this to standard notation. If I convert this to standard notation, that's going to have to go back 1, 2, 3 places. Okay, so that's how much each person has to pay, or about $2,700, and if we round, $65. So each person would have to be responsible for $2,765, and that would pay off that country's national debt. So that's what we did, and that makes sense because we're taking that debt and we're dividing it among the entire population. So it's going to be dramatically reduced. So everyone all right with that one? And on these, again, they want it in scientific notation. I convert it to standard because in standard notation, we understand what this is. Okay, this makes sense. This, in a lot of cases, does not. So I like to convert things so that it makes sense. So you can see that's, about basically $2,800. We do have a few questions out of 4.4 to look at, and 4.4 is going to be the more important section. We use exponents quite a bit in college algebra, but we really, really need to make sure that we know how to multiply these polynomials, because we're going to be using it a lot in this class, and we're going to pick up in college algebra with multiplying polynomials. So we're going to begin in 4.4 with question 2. And we've got a minus 2x plus 4y. And we're going to multiply that by 3x plus 11y plus 1. When I look at this question, I first need to see how I'm going to approach it. Now, if it's a 2 by 2, a binomial times another binomial, I could use the FOIL method. Right? But this is too big because this has 2 terms and this has 3 terms. So if it's too big to FOIL, what we do is we use the box method. Box or the rectangle method. So we create a rectangle. Now, it doesn't matter which one goes across the top and which one goes down the side. That's not important. It's just that one goes across the top, one goes down the side. If you make the larger one go down the side, your rectangle is just going to go this way. I usually like to make it go left to right. So I'm going to write the larger one across the top and the smaller one down the side. And that's going to make a grid. And you could do this just by distributing through and keeping track of the terms. All this is a visual way of doing it. It makes sure we don't accidentally miss a piece. So now we fill it in. And we multiply our numbers. Exponents add together. So minus 2 times 3, that makes it a minus 6. X times x, that's an x squared. Next, minus 2 times 11, that's a minus 22. And the x and the y are linked together. And then we've got minus 2x times 1. So that's a minus 2x there. And now we repeat the process on the next row. So on the next row, we have 3 times 4. That makes it a 12. xy. Then we've got 4 times 11. That's a 44. Y times y. That's y squared. And then we have 4y times 1. So it stays the same as 4y. Now we put these together. And when we put these together, work in the upper left corner. Upper left corner is a minus 6x squared. So that's going to be gone there. Now these can go together. So this diagonal, they can go together. They're both xy, so we combine them together. Minus 22 and a positive 12. Well, that makes it a minus 10 when we add them together. xy. Gone and gone. Now be careful because the minus 2 and the 44, they cannot go together because one's got an x and one has that y squared. So they have to be written separately. So that's a minus 2x and then a positive 44 y squared. Gone and gone. And then what do we have left by itself? 4y. Now the order is not that important. Okay, if you put them in a different order, that's okay. Just make sure all the pieces are there. So if you wrote that 44y squared first, and you wrote it with the y's going down in power first, that would be okay. Just make sure all the numbers are there. Question 6. So for question 6, we've got a minus 11 ax squared out in front. And then we have a minus 11 ax to the 4th. A plus 7 x cubed. And a plus 4. Well, we're not going to have to FOIL. We're not going to have to use the box method, right? Because all we have to do here is what? All we have to do is distribute. So this is going to get distributed through. That's it. No other parentheses. So we just simply distribute it through each piece. Now the exponents again are going to add together and numbers are going to multiply. So when I distribute through negative 11 and another negative 11, that makes it 121, I believe. Yep, 121. And that's going to be positive. How many A's do we have? We have an A and another A. That makes it an A squared. What about the X's? We have 2 and 4 more. Then makes it X to the 6th. Next one, we've got minus 77. We've got an A. And how many X's? We have 2. And 3 more makes it X to the 5th. And then the last piece we're going to distribute through. And that's going to make that then a minus 44. No extra A's, so it's just an A. And no extra X's, so it's just an X squared. And that's as far as we can go. Now, how do we know that we can stop here? Well, these are all different, right? They all have different exponents, so nothing can be added together. Nothing goes together, so we know that we are then done. So distribute it through, multiply those coefficients. Now, the coefficients are the numbers out in front. Exponents are these powers here. Exponents add, coefficients multiply. Question 7. We've got 4 m to the 4th, z to the 4th, and we've got 3 m cubed, z squared. When I look at this, do I have any addition or subtraction at all? No. No addition, no subtraction. It's just this piece multiplied by this piece. So that means we just multiply the numbers, add the exponents. Because no addition, so we don't have to distribute it through. Right? This one had the addition subtraction, so we had to distribute it through each piece. Okay? This one does not. It's one whole term. Terms are separated by addition or subtraction. So this one has no terms. Right? Well, one term in each one. So they multiply together. So 4 times 3 is 12. M, we're going to add them together. We have 4 and 3 more makes it 7. Z's, we have 4 and 2 more makes it 6. So my final answer would then be 12 m to the 7th, z to the 6th power. And that's it. Okay, that was question 7. We've got a couple more to look at, and then we'll take a short break, come back, and talk about factoring. Chapter 5 is going to be the last chapter that we go through, but it's one of the most important, and we're going to spend a lot of time in Chapter 5. So let's go ahead and finish these up. We got 2 more to look at. We just did question 7. So we've still got 9 and 10 to work through. So question 9. It's kind of similar to what we just did, but this one has 2 terms. So unlike the last one, we had no addition or subtraction, so we just multiplied straight across. Now this one has 2 terms. And terms are going to be separated by addition or subtraction. So we're going to distribute this through this piece and also this piece here. So 2 times a negative 5 makes it a negative 10. And how many x's? We have 5 and 1 more makes it x to the 6th power. And then we have 2 times 6, that makes it a 12. No x's, to combine, so you'll leave it as x to the 5th there. Yeah, a lot of these aren't too difficult to work through. I think 4 is a pretty easy section. Some of them may take a little bit of time if you have to use the box method, but they're not difficult. It's just keeping track of the signs and make sure you multiply and add correctly. Question 10 is a little bit different because of the decimals, and also because we have to write it out. This is a type of question that I see students make a mistake on all the time when they get to college algebra. A lot of times students will think that I can just distribute that square through each piece. And you can't really do that because you're going to be missing the middles. So what we have to do to get our 3 terms out is we're going to have to rewrite this. And we're going to have to rewrite this as 0.6 x minus 1.1y times another 0.6x minus 1.1y. Wrote it out twice, and now we're going to use our FOIL method. So whenever you have parentheses, you've got to write it out. If this would have been a cube, you'd write it out 3 times. All right, this one just squared, so we write it out twice. Now we have 2 terms by 2 terms, so we can apply our FOIL method. And that's just simply multiplying it through. So let's go ahead and do that. We'll use a calculator. Okay, for these decimals, so we have 0.6 times another 0.6. That makes it a 0.36. X times x makes it an x squared. First times first. Okay, we did that. Outside times outside, which is here. So let's do it next. So 0.6 times 1.1. We know our sign's negative. So that's a minus 0.66 xy, it looks like. Then we do the inside times the inside, which is another minus 0.66 xy. And then finally, watch your signs on the last one. Negative and negative makes it a positive. So that's 1.1 times 1.1. And that's a positive 1.21y squared. And what do we know? Well, in this case, we're in luck because the middles can go together. So now we can write that as 0.36 x squared. And then we've got a 0.66 and another 0.66. So that's a minus 1.32 xy. And then a positive 1.21y squared. And that is going to be our final finished answer. All right, is everyone okay with that so far? All right, so we just wrote it out twice, distributed through, and that gave us our final answer there. Let's go ahead now and take a short break. We'll meet back at 9:30, and we're going to start factoring. Factoring is one of the most important concepts that you need to be really good at for college algebra. So we'll be back here in about 10 minutes, and we'll start